If you've ever stared at a valence bond theory question on a chemistry exam, you know the drill. Writing out full electron configurations and mapping out hybridization takes time. But there is a specific method to determine donor types and spin states without the usual long-form work. Start by identifying the donor atom on your ligand. If it's sulfur, a halogen, or oxygen, remember the acronym SHO. These function as weak ligands, meaning they won't force the central metal's electrons to pair up. In contrast, if your donor atom is nitrogen, carbon, or phosphorus, NCP, it's a strong ligand. These supply enough energy to force those electrons to pair together. Next, find the metal's remaining electrons using a single calculation. Take the atomic number, subtract the oxidation state, and subtract 18. This gives you the count for your d orbital immediately. Combining these donor rules with the formula allows you to determine the hybridization and spin state for standard coordination complexes without drawing every subshell from scratch. Let's apply this to the tetrachloridonickelate ion. Nickel's oxidation state here is +2. Its atomic number is 28, -2, -18, which leaves us with exactly 8 electrons. The ligand is chlorine, a halogen. Following the SHO rule, we know it's a weak ligand. It won't interfere with the electron arrangement in the metal's orbitals. We lay out the d, s, and p orbitals and drop those 8 electrons into the d boxes. Because there's no forced pairing, the electrons spread out, leaving 2 of them sitting alone. Since we have 4 chlorine ligands, they occupy the next available empty slots, 1s and 3p orbitals. This results in sp3 hybridization and a tetrahedral geometry. Since unpaired electrons remain in the d orbital, the compound is paramagnetic and categorized as a high-spin complex. Now look at this iron hexacyanide complex. Iron's oxidation state is +3. Atomic number 26, -3, -18 leaves us with 5 electrons. Cyanide has a carbon donor, putting it in the NCP category. This strong ligand forces the metal's electrons to pair up to make room for itself. Instead of spreading out across the 5 d boxes, these 5 electrons are packed into the first 3. This leaves the last 2 d boxes completely empty. The 6 cyanide ligands move into those 2 empty inner d boxes, then the s and p orbitals. This creates d2sp3 hybridization. Remember this with SILO. Strong ligands use inner orbitals, resulting in low spin. By utilizing those inner d orbitals, the compound exists in a low spin state. Now apply these steps yourself to this cobalt hexafluoride complex. Determine the oxidation state of the central cobalt atom and use the SHO and NCP rules to decide if fluorine is a weak or strong ligand. Pause the video and write down your answer. Actively applying the logic now ensures you can replicate these steps during an exam. Cobalt's oxidation state is +3. Its atomic number is 27. So 27 -3 -18 leaves us with 6 electrons. Fluorine is a halogen, making it a weak ligand. It won't cause pairing, so the 6 electrons stay spread out. The incoming ligands are forced to use the s, p, and outer d orbitals, creating sp3d2 hybridization. Finally, we calculate the magnetic moment. We use the formula mu equals the square root of n times n plus 2, where n is the number of unpaired electrons. We have 4 unpaired electrons. Plugging that in gives us the square root of 24 Bohr magnetons. From here, you can also find the spin multiplicity by using the 2s plus 1 formula. These calculations confirm the magnetic properties of the complex, providing a numerical way to verify the orbital arrangement you've predicted. This summary compares the 2 pathways. SHO ligands are weak, leave electrons unpaired, and use outer orbitals. NCP ligands are strong, force pairing, and utilize inner orbitals. Save this logic tree for your study sessions. Mastering these relationships allows you to solve for hybridization and magnetic nature quickly and accurately.